Hello, welcome to the Integration Methods Review video. Today we'll be going over the methods of integration, including integration by parts, trigonometric integration, trig substitution, finding the length of an arc, and partial fraction decomposition.
First problem that we're going to do is a fairly basic integration by parts problem. So problems of this form, like x to some power multiplied by some other function, are a common one you can solve with integration by parts. Because if you just keep taking derivatives of the x, then eventually it'll become 1, and then you can just integrate the other function. We're going to split this out. So we can set u equals x, and then dv equals e to the x dx. And we just take the derivatives of both, or we take the derivative of the u equation. So du over dx equals 1. And then we can rewrite that as du equals dx. Now for the v side, we just integrate both sides. Integral dv is v, and integral e to the x dx is e to the x. So we can rewrite this as integral of u dv, and by integration by parts rules, we can change that to be uv minus integral of v du. And then u equals x, v equals e to the x, so we get x e to the x minus integral 1 times e to the x dx, which is just x e to the x minus e to the x plus c. So the next one we're going to be looking at is integral of secant cubed x dx. This one is a bit of a trickier integration by parts. It also covers some of the uses of trig identities in solving integrals. So how can we attack this? Well, the first thing we can do is split it up into two parts. So if we look, secant squared is the derivative of tangent. We can find the derivative of secant. So this is a prime candidate for integration by parts. Now we just take the derivative of u and take the integral of dv, and we rewrite according to integration by parts. Now, at this point, some of you might be screaming out, "Oh, we can just take the integral of tangent secant x." But the problem is that will bring us exactly back to where we started in the loop. We have to take a different approach, which is splitting this out using trig identities. We can rewrite that as... Now, we have an interesting thing here. The term which we started with has appeared in the answer. Now, if we just kept, we could certainly use the same process again, but then we just get more terms and go so on an infinite loop. What we have to do is a tiny bit mind-bending. We just need to move this down here to get... Now we have an equation instead of an expression. We can add this to both sides. So then we have our answer, we have to divide by 2. And then the integral of secant is one that you can get from a table. Done. Okay, so the next problem we're going to look at is this integral. Now, when you see this, your instinctual reaction might be to use u substitutions and arc sign to solve this. But we're going to talk about doing it in a slightly different way, using trig substitution. It's a bit more of an involved way, but it's also a lot more general. It's really good at handling these three things when they appear in problems. What you do is you imagine that you have a triangle with angle theta. In this case, we have a product of we have a thing of the second type in the denominator, 9 minus x squared, so we have a equals 3. Let's say we define theta such that sine theta equals x over 3. So that means that our hypotenuse is 3, and one of our sides is x. So if we take the derivative of this, then we get cosine theta d theta over dx. We take the implicit derivative, equals 1/3. So we're preparing for the substitution. The other thing we have to do is find the length of this side, a. So by Pythagorean theorem, a squared plus b squared equals c squared. A equals 9 minus x squared square root of that. So as you can see, this pops up here. That's how this is connected. So if we find the cosine of theta, it's just a equals square root of 9 minus x squared. Cosine of theta equals 1/3 square root of 9 minus x squared. So this whole thing in the denominator is equal to, so 3 cosine theta equals square root of 9 minus x squared. So we replace dx with 3 cosine theta d theta, and 1 over 9 minus x squared with 1 over 3 cosine theta. So as you can see, this and this cancel out. We are left with integral 1 d theta, or theta. And then if sine theta equals x over 3, then theta equals arc sine of x over 3. This is our answer, plus c. The next thing that we're going to do is a bit of a change of pace. We're going to do a proof. And we can prove that the circumference of a circle is 2 pi r. I mean, I know that you all know that. This is like elementary school material, but the tool calculus and arc length gives us an interesting new way to prove this thing that we already know. So if we have a circle like this, now the equation for just this half of the circle is square root of r squared minus x squared, where this is r. So we can actually find the arc length of this equation, and that arc length should be half the circumference of a circle, or 2 pi r. So the arc length should be pi r. So how can we do that? Well, the standard arc length formula is integral from integral from a to b of square root 1 plus dy over dx squared dx. Now that's not the second derivative, that's the square of the derivative. Notation is confusing sometimes, but that's how it goes. So the first thing we're going to do is find dy over dx. That's just a pretty simple application of the chain rule. And then dy over dx squared. I like to do this outside of this integral just so we don't have to write so much other stuff while we're simplifying this. Equals, and then these cancel. X squared over r squared minus x squared. And then dy over dx squared plus 1, because that's what's inside the integral, is x squared plus r squared minus x squared over r squared minus x squared. Now, how can we evaluate the square root of this? Well, we can do a really simple simplification, which is just getting rid of this. Now we put this back in our integral. So our bounds are from negative r to r, and we want the square root of r squared over r squared minus x squared, because that's what dy over dx squared plus 1 is, dx. So that's integral from negative r to r of r over square root of r squared minus x squared dx. Now this here is more or less the same trig sub as we saw in the last one. I'm just going to do that really quickly. So we get that r cosine theta d theta equals dx, and r cosine theta equals r squared minus x squared. So you might be tempted like, well, wait, what about the r on top of the thing? Well, you have to be careful because that r is actually a constant, and we can just leave it there. We can actually factor it out if we want. R, negative r to r, and then r cosine theta over r cosine theta. d theta. So these just cancel out, and we get r negative r of 1 d theta. And then that's just r times theta from negative r to r. However, we have to be a little careful because those are not theta equals r, they're u equals r. So we can't substitute those in until we've converted back to du, not u, not theta. So r, so then theta equals arc sine of x over r. So from x equals r to x equals negative r. So r over r is 1 minus sine negative 1 of negative 1, which is just r of pi over 2 plus pi over 2, aka pi r. And this is the half circumference. Circumference equals 2 pi. Okay, so the last problem we're going to look at is one that involves parallel fraction decomposition. So commonly in calculus, we have to integrate things that have polynomials in the denominators where the degree is higher than 1, like this one, which is x squared. You also get x cubed, x to the fourth, and such. So we can integrate polynomials that have like x to the first degree, but we can't directly integrate ones like this. In order to integrate them, we have to split them out using fraction decomposition. So first step in doing that is, of course, factor the denominator. 4 over x minus 1 times x minus 5. And then to decompose into partial fractions, we need, so the partial fraction theorem guarantees that for an equation like this, there are two fractions in the form of a over x minus 1 plus b over x minus 5 that we have to do, or that we can make. So the only thing we have to do is figure out what the a and b are. So if we add these two fractions together as they are, we get ax minus 5a plus bx minus b over x minus 1, x minus 5. So we know that a and b are such that this whole business equals 4. So then we can set up a system of equations to figure out exactly how to do that. So you know that ax and bx have to add up to 0x because there's no x term there. So a plus b equals 0. And then we also know that negative 5a and negative b have to add up to 4. Now, how can we solve this exactly? Well, we just have to add these together. So we know that a plus b equals 0. So a equals negative b. We can substitute that in to get 5b minus b equals 4. 4b equals 4. b equals 1. So therefore, a must equal negative 1. So now, we just plug that in here to get, so a over x plus 1 becomes negative 1 over x minus 1 plus 1 over x minus 5 dx. So then, all that we have to do is integrate these. So we do some sort of implicit u subs here. So for the first one, it would be u equals x minus 1. And the second one, it would be like r equals x minus 5. We can sort of do that in our head to get negative ln, absolute value of x minus 1, plus ln, absolute value of x minus 5, plus c. So now we're done.